So at this point, you should be able to stop your video and answer the following review questions. So these are things you should be actively doing on your own, not just skipping forward to see what I have to say about it. So first, make sure you understand how do you prove that a set A is open, what the logic would be behind that. Although we have not done an example yet, we will. Then ask yourself, how do you prove that A is not open? Then, what about the empty set? Is the empty set open? And we also know that open intervals are open because they don't contain their endpoints. But can you actually verify that the definition of an open set holds when you have just an arbitrary open interval AB? So I pause the video and make sure that you can answer these questions, and then we'll go over them. Okay, so how do you prove that a set A is open? You would let little a and capital A be arbitrary. And then you would have to find epsilon greater than 0 such that V epsilon of A is contained in your set, capital A. And how do you prove A is not open? You would find a little a in A such that for all epsilon greater than 0, V epsilon of A is not a subset of A. Is the empty set open? The answer is yes, vacuously. Whenever something is vacuously true, it's simply because you can't show it's false. So if I wanted to show that the empty set was not open, what would I need? So that's a good question. I'm going to write that down. So to show that the empty set is not open, what would we need? Well, take a look at the answer to number 2. We just answered that. We would need to find an element of the empty set that has no epsilon neighborhood that stays in the empty set. So we would need an A in the empty set. But regardless of the things that need to be true about that A, the point is we would first need to have an element in the empty set, which we can't have. So we would need an A in the empty set, and I mean, you could say such that every V epsilon of A is not a subset of the empty set. But in particular, there is no A in the empty set. Therefore, we have no candidates for showing that the empty set is not open. So, the empty set must be open. Okay, so then can you prove that any open interval AB is an open set? So really what we're saying is take a look at a picture. You've got your open interval, so here's A, here's B. I'm going to go right up to but not include the endpoints. Then if I'm going to prove that this is an open set, I need to choose an arbitrary point in my interval and demonstrate how you would get the epsilon neighborhood that you know works for that point. So let's say I picked, say, this value. Now, since A already has another role in this problem. I'm going to call this point X. And I throw X down into my neighborhood or into my set, and I say, all right, here's my arbitrary X. What should epsilon be? And what you should be thinking is, well, I need to figure out which endpoint X is closer to and make sure that I don't choose an epsilon neighborhood that passes that endpoint. So in this case, when I look, I see X is closer to A. So if I measure the distance from X to A, that would be a valid way to choose my neighborhood. In general, what we're doing is we're saying, given X, find the minimum of the distance from X to A and the minimum of the distance from X to B. And let that be your epsilon. So if I was going to write a proof, I would say, let X in my open interval AB be arbitrary. And then I'm just going to let epsilon be the minimum distance between X and A and X and B. Now, since I know the way that my points are ordered, I don't need to use absolute values here. The distance from X to A is going to be X minus A, and the distance from X to B is going to be B minus X. By construction, if I pick any, say, y in V epsilon of X, y is going to have to be in my open interval AB. So what I've established here is that V epsilon of X, for the epsilon I've selected, is a subset of AB. And this just means that by definition, AB is open. Now, the next two questions I would like for you to answer, ideally it would be awesome if you could chat with your friends some way about this. I don't know if you want to use Zoom or what you want to use, but here's my question. So, example. Suppose that A and B are both open. I want you to answer the question, must A union B be open? And must A intersect B be open? So as a first step when you're getting started, make sure that you understand what it means to say that A union B is open and what it would mean to say that A intersect B is open, and then figure out whether or not you believe it. Can you prove it? Can you come up with a counterexample? What's bothering you? So take a moment to do that. It may help because we're used to thinking of union and intersection as Venn diagrams. It may help to show you a way that I could make a two-dimensional picture demonstrating openness. The point is here I have a set A. It's represented by a circle. So here's my set A. I pick a little point A inside of it, and I should be able to put an epsilon neighborhood around that little A such that the entire neighborhood around it stays inside my set. So that's kind of like coming up with this ball or circle that you can put around it. And so this is this radius right here is epsilon, and overall this is my epsilon neighborhood, and it stays entirely inside A. So maybe you might try to draw pictures of the union and the intersection and think about what it would take to, get a radius that might allow a point in the union to stay in the union, or a point in the intersection to stay in the intersection. So let's take a look at the union. If I'm talking about the union, then I am dealing with the entire collection of any point that sits in A or in B. So I shade both regions. So if I select a value X in A union B, if I'm going to claim that this set is open, then I would need to be able to find a neighborhood around that point that stays entirely inside the union. So I pick an X in the union, and that means that X is either in A or it's in B. So let's say I chose my X. Here it is. Why would, so in this case, X is in A. Why would it be that I can get an epsilon neighborhood? Well, since X is in A, I know that there's a neighborhood around X that lies entirely inside the set A. So here, this is my epsilon neighborhood, and I'm getting it, maybe I'll put a subscript on it, I get it from capital A. So since A is open, any X that sits in A will have epsilon A greater than 0, such that V epsilon A of that X you've selected lies entirely inside A. Well, why do we care? The answer is that if you get inside A, then you're certainly in the union. The way you get in the union is to be in one of the sets, or at least one of the sets. So since A is a subset of A union B, we would have to get that V epsilon A of X is contained in A. Would anything be different if X had been in B instead? What if I had some other X and it was here? Well, the fact that it's in B, again, doesn't matter. B is open, and so I could get the epsilon B. So here, this would be radius epsilon B, and I know V epsilon of B has to stay in the set B, using the fact that B is open. So what I get is that the argument is the same, regardless of whether or not X is in A or X is in B. I mean, if X is in both sets, then you could use either of the epsilon values. It wouldn't matter. So let's write up a proof for this. So our claim is A union B is open. And just as a reminder, what we would need to demonstrate this is we need to show that for all X in the union, there exists an epsilon greater than 0 such that V epsilon of X is entirely contained in the union. Okay, so here's our proof. So let X be a point in A union B. Now, just to point out here, we are assuming that A union B is non-empty. If it were empty, then the set would be vacuously open. We've already handled that case. So we typically only restrict our arguments to dealing with non-empty sets. So pick an element X in the union. Then that means X is in A or X is in B. Because either case results in an analogous argument, we can say, without loss of generality, assume X is in A. Since A is open, there has to exist an epsilon greater than 0 such that V epsilon of X is entirely contained in A. Since A is a subset of A union B, V epsilon of X has to be contained in A union B. By definition, A union B is open. You might go back up to the claim. When we say A union B is open, it is important to note here this is when A and B are open. You need to know that since that's how we get our epsilon neighborhood. So we've now shown that if two sets are open, then their union has to be open. But does it matter how many open sets we union? Could I union 5 open sets and would it still be open? Could I union infinitely many open sets and would it still be open? And so to answer that question, we look back at how our argument worked for two sets. So notice that when we chose an element in our union of all the sets we were dealing with, that meant that that X value had to be in at least one of the sets. So we start with an X in the union and then we figure out locally which open set it sits in. Once we're in that set, we borrow the epsilon neighborhood that we get from the fact that that set, that single set, is open, and then we just include that back into the union. So the answer here is no, it doesn't matter how many there are. So the union of an arbitrary collection of open sets is open. The idea is you pick X in your union, so maybe I denote my union, maybe my sets look like some like AN or something like that. That implies that X is in some AI. So AI being open implies that there has to be some epsilon such that V epsilon of X stays inside AI, but AI is just a subset of the union. Okay, so let's return to our question about intersection. So if A and B are open, must A intersect B be open? Okay, so now what if A and B are open? Does that mean that the intersection of A and B has to be open? And really what we're asking precisely here is if I pick any X in the intersection, does there have to exist an epsilon neighborhood around that X that stays entirely inside the intersection of A and B? Well, my given information right now, I just know that A and B are open. And if I pick an X in the intersection, I'm in A and I'm also in B. Now, because X is in A, I know that there's this epsilon neighborhood that I can put around X that should stay entirely inside A. I'm going to label this radius epsilon sub A, like that. So what I'm pointing out here is that because A is open and X is in A, there has to exist a V epsilon A of X that's a subset of A. Now, remember, I'm in the intersection, which means that I'm also going to be a member of the set B. Now, I get a different epsilon radius locally from X sitting inside B because B is an open set. And notice that the epsilon that I'm able to draw here is going to have to be a little bit smaller than epsilon A because X is a little bit closer to the boundary of B than it is to the boundary of A. And so here's my radius, that's my radius epsilon B. And so coming down here, I have that because B is open and X is in B, there has to be this V epsilon B of X that's contained in B. So then this begs the question, how do I choose my epsilon value so that I stay in both sets because I want to remain in the intersection? And if you look at my picture, you can see that the green neighborhood associated with A does not lie inside inside the set B. We've got here highlighting that portion. We've got this piece right here, right? That leaves the set B. And so that tells me that epsilon A doesn't work. But if we take a look at epsilon B, that neighborhood stays entirely inside the intersection. So then we have to ask ourselves, in general, how would we pick? So given epsilon A and epsilon B, how should we choose epsilon such that V epsilon of X is a subset of the intersection? Well, going back up here, epsilon B was the right choice for this picture based on the X that we selected because epsilon B was the smaller radius. So in general, we would want to let epsilon be the minimum. The idea that we're using here is the following fact, and this is important. So, fact. If V epsilon of some number X is contained in A, then V epsilon prime of X will be contained in A for all epsilon primes that are less than or equal to epsilon. So what I'm saying here is that if one epsilon neighborhood works, then any radius smaller than the epsilon you've selected should also work because you're just creating a subset relationship. If you want to see what I mean by a picture, let's put a X right here. Let's say that this is my epsilon neighborhood. As long as I pick any other radius that is smaller than epsilon, I'll have containment. So maybe I pick this one, and that's my epsilon prime. Oops. Okay, let's write up our proof here. So again, our claim is that if A and B are open, then A intersect B is open. So proof. So we assume A and B are open. And remember the quantified statement that we're proving. We're trying to show that if I pick an arbitrary x in the intersection, that there exists an epsilon neighborhood that stays in the intersection. So I'm going to let x in A intersect B be arbitrary. Then remember what that means, just based on the definition of intersection. X has to be in A, and X is also in B. Since A is open, there exists an epsilon A greater than 0, such that V epsilon A of X stays inside A. And since B is open, there exists epsilon B such that V epsilon B of X stays inside B. Now we are ready to introduce our epsilon. We said that epsilon, the one we want for the intersection, is going to be the minimum of these values. And so, since epsilon is less than or equal to epsilon A, V epsilon of X has to be contained in V epsilon A of X, using that fact we just wrote down. If you use a smaller radius, you're just creating a neighborhood that's a subset. But that neighborhood, epsilon A, we know is a subset of A. And then similarly, epsilon is less than or equal to epsilon B. So V epsilon of X is a subset of V epsilon B of X, which is a subset of B. And now what we've shown is that the epsilon neighborhood is a subset of both A and B. And that's another way of saying that you're a subset of the intersection. So thus, V epsilon of X is a subset of the intersection. And we have just demonstrated that an arbitrary point always has an epsilon neighborhood that remains inside the intersection. That's the definition of being open. Okay. So remember when we asked the question about whether or not the union of two open sets had to be open, we then, when we were done, we asked, did it matter how many sets we were unioning together? So I want to ask that same question here. Does it matter how many open sets we intersect? Will the intersection still be open? And to answer this question, we have to go back and remind ourselves what our argument hinged on. We said that finding our epsilon all came down to being able to choose this minimum value. You took all the sets involved in your intersection, you got all of their local epsilon neighborhoods that remained in those local sets, simply because locally the smaller sets are open. And then we had to take their minimum. And So what do we know about minimums? We know that in general, we cannot guarantee that a minimum, or essentially that an infinite list has a minimum value. That an infinite list of epsilons if I had a bunch of different sets, I'd have like epsilon 1, epsilon 2, epsilon 3, etc. And I'd be looking to find that minimum. But what if the infimum of these values is 0? That's not a valid choice of epsilon. So it turns out that it does matter. The theorem that we're able to get instead here is that the intersection of finitely many open sets is open. And to add to the theorem, the union of an arbitrary collection of open sets is open. So the reason why we're able to only do finitely many is because that's the only case where we can guarantee there's a minimum epsilon. So finitely many means where this guarantees there exists a min epsilon value.